So my name is Jonathan Byrne. I'm from the Urban Modelling Group in UCD and also co-founder of the 3D Printing Centre there. And today I'm going to talk about automatic optimization in additive manufacturing. So with 3D printing, we have complete control over the placement of material in the design. And so what we can do is very selectively remove and add that material to optimize designs in a way that wasn't possible before. So to give you an example of this, we look at evolution. So this is a bone from a bird's wing, and evolution is one of the best optimizers. You can see over millions of years it's removed all the excess material. It's trying to optimize the design to both make it lightweight and strong, and these are two conflicting objectives. So this is the design it came up with, and traditional manufacturing techniques wouldn't be able to generate that design. 3D printing can. 3D printing has no problem doing it. So, what are the advantages of additive manufacturing? First and foremost, there is no complexity penalty. A 3D printer can print a solid block of metal as easily as the most complex fractal design you can think of. It doesn't care. It is just melting the material as it's building it up layer by layer. There's no machinability issues. So, you can, traditional machines have tooling, and those tools can get damaged as they're machining it. There's very few moving parts in it. It's a laser melting layers of powder, so by building it up, there's no machining issues at all. And finally, customized components. A 3D printer can print 50 different objects as easily as 50 identical objects. So this naturally falls into the ability of it to rapidly prototype and generate improved iterations of a design. So just to look at some of these things, this is a radiator that they developed for a car, and you can see that it has very complex designs and a complex internal structure. So that's not possible with standard manufacturing techniques. CNC machines can't machine inside the components. 3D printing can. And in this design it uses heat turbulators. So these basically mix the water as it flows through it. It generated much more efficient heat transfer, and it was a much improved design. This is an example of how well the machinability works in 3D printing. This is a rocket engine by SpaceX. It's printed in Inconel. It's a nickel chromium superalloy, and it is very difficult to machine. Traditional tooling, once it works the part once, it starts hardening, and it means that it can't be successively manipulated and machined as using traditional CNC approaches. With 3D printing, because you're just melting the powder, build it up layer by layer, and you get improved designs. Also, specifically with customization, medical implants are hugely benefiting from this technology. First of all, you can customize the component to the person. Every person is different, every injury is different, so the implant should be customized to them. Secondly, you can control, you can increase the surface area, you can make the parts hollow. This allows for, in these sort of hip implants and knee implants, it allows for greater area for the bone to knit onto the parts, and also it allows for increased blood flow, which improves the recovery of the patient. But these are all the approaches. Why would we want to optimize the design? Well, it's the main advantage of 3D printing. You can remove excess material, which will lead to monetary savings. So for space applications, if you're going to the ISS, each kilogram costs $60,000. To get it into low Earth orbit costs up to $7,000 per kilogram. A more practical example would be in aeronautics. Each kilogram costs €30,000 over the cost of the aircraft lifespan. That's a saving in fuel alone, only fuel, in over 30 years. And finally, automotive. If you take 50 kilograms off the weight of a car, it improves the fuel economy by 2%. Again, over the lifetime of that vehicle, that adds up to be a massive improvement. There's no complexity overhead, if I'm repeating myself. This is the main advantage of 3D printing in manufacturing. If you use CNC machines to manufacture a part, the more complex it is, the harder it is, the longer it's going to take to manufacture it. With 3D printing, that it no longer applies. And it also allows for rapid design iteration. So you can generate your design, you can test it destructively or non-destructively, you can validate it, and very quickly have a prototyping process that rapidly iterates through designs. We've found this in our 3D printing center. People come back to us week after week, and we just start firing the designs back out to them, and they'll come back with revisions and improvements based on what they've already tested. So it naturally lends itself to optimization. So here are some examples, real-world examples. This is a hinge cover off an A380. This was the first practical 3D printed example that was used in production. As such, it was tested to death. 3D printing has been in aircraft manufacturing for at least 30 years, but this was the first one where it was a high-risk application. It saved 10 kilograms of weight in the entire aircraft, which equated to a saving of 300,000 on the cost and fuel economy of the aircraft over its lifespan. This is a tensegrity structure that Arup developed. This was in The Hague in the Netherlands. And when a tensegrity structure is a tensional integrity structure, instead of using compression, it uses beams and elements that are in tension to hold it together. But to connect them, they needed bespoke connectors for the wires. They worked out that they'll have to manufacture 1,200 of these, each of them individually manufactured, each of them tested and validated. And they thought 3D printing might offer a better solution. What they found was that they could take the loading conditions and use that to generate optimized designs. This is an example of one, and this is using less material, but still has the same material strength. Another addition was that when they first developed it, the one in the middle was the first optimization. When they did further optimization and tried to compress the size of it, they could keep running the algorithm and get better and better improvements on the design. This is one that was done with the hydraulic manifold by EOS and Within Labs. So instead of starting with the solid block and working backwards, they started with the hydraulic manifold that they wanted and then built outwards. And here they did a two-mesh approach. So they had one mesh here that would hold it very firmly in place, and then they meshed that mesh onto the frame. So this again produced 60% less material than the standard approach. So if you want to do this, you need to be able to analyze the model. So normally finite element, FEM, or computational fluid dynamics will give you an analysis and basically feedback on the model design. Most people are already using this technology, so if you are designing an analysis or SolidWorks, you can either plug it into a finite element model, or they'll have a finite element software built into the software. And if you've done that already, you've already got half what you need to do the optimization. The other part is an algorithm that will iterate and improve the model. So I'll just go over some of them. So one very popular one, it's been around for 40 years, is the evolutionary algorithm. And with an evolutionary algorithm, you tell it what to do, not how to do it. And basically what it'll do is it'll guess. So it'll make 100 guesses, and 99% of them will be terrible, but 1% of them will be slightly better. Has that crashed? It has. Started up again. There we go. That's running live, by the way. So here we're trying to evolve a small car. The blue wheels will move and the red wheels can't touch the ground. And most of the designs will be terrible, but one of them will be good, and it will keep choosing that, remixing it with other good designs and mutating it, and eventually it'll come up with a very good design. An example of these in practice, this is the Shinkansen train in Japan, and this is the evolved design. Again, they're very non-intuitive approaches because it has no idea what it should look like. It's literally starting with guesses and then building on good guesses. This is a NASA antenna for the ST5 space program. Again, very non-intuitive, but it outperformed the traditional designs. In fiber optics, the standard approach here is line them all up. And these were the evolved approaches. Again, there was a 30% improvement on data transmission. Where this falls down, though, is when being applied to 3D printing, we normally use what they call a direct mapping. So voxel, a volumetric pixel approach, where they essentially build a model out of Lego and allow the algorithm to optimize that. Unfortunately, it doesn't work very well for 3D printing. Here's another example where they literally evolved Lego to try and evolve a bridge. It worked, but you'll see that there's little pieces here and there that actually add nothing to the design. And so when using a direct mapping with an evolutionary algorithm, it doesn't work for optimizing 3D printed shapes. The next approach is topology optimization. So with this, you're taking the finite element model and you're removing the pieces that have the least stress and the least strain on them, and it'll generate a design. These are far more, evolutionary algorithms are much more stochastic. They're not random, but it's guided randomness. Whereas this is a far more deterministic way of generating a design. The problem is as you scale up the design, it has to recompute the FEM analysis every single iteration. So each time it's removing a piece, it's doing it. As you add more and more complexity to it, the time it takes to compute it increases cubed. We're looking at using GPUs to optimize them, and now we're getting to a point where we're getting optimized designs that have sufficient resolution that they're actually matching reality. So the final approach is parametric design. So with a lot of software now, SolidWorks, CAD, they're introducing a parametric model. There's also Bentley systems, generative components, and with it, it's much more like design by spreadsheet. So instead of just putting the blocks together or putting the walls of a building together, you define the relationships, like in a spreadsheet where you have the numbers and the relationships between the numbers. So when you change one, the change ripples through the model. And while this takes a little more time initially to generate your design, it allows you very quickly to change and iterate. So this is an example of some parametric software. It's Vehicle Sketchpad by NASA. And it allows you to, once you've defined the wing, the body, it very quickly allows you to generate variations in the design. So what we're doing is combining parametric models with evolutionary algorithms to generate optimized designs. Some instance of this is the Turning Torso Calatrava. Architects love this because they can very quickly, once they have their model, if the customer needs an extra floor, they just change it. If they don't like the angle, they can change it. And they can very quickly, rapidly iterate through designs. And where you'll see this in optimization software is with Within Labs. They use a parametric model combined with an optimizer to generate their optimized lattices for medical components. So, what are the problems of this? We've got all these wonderful models and all these optimizers, but the problem is that they're not accurate enough. All models are wrong. By definition, a model is stripping out and removing information. So what you want is a model that is fast but accurately represents the production. What we've found is that a lot of these optimizers, when you actually print the part, it doesn't match reality. So one big problem we came across is this one, the 99 line problem. So in 2001, Ole Sigmund wrote a paper showing how easy these approaches were. Coded 99 lines in MATLAB and said, here you go, this will do topology optimization. And it just to kind of show how easy it was. The problem was that everyone started using this piece of code. And it became an arms race where they started trying to get 88 lines of code. Or all these optimizers are written for in academic purposes of minimizing the code, the lines of code, which really has no ramification on anything. What you want is something that will actually generate a decent working valid design. So a lot of our work at the moment is building FEM models that will work with 3D printing. Even with GPU models, they're still talking about lines of code. Another issue is that a lot of these people who are doing these solvers are using GPUs, standard GPUs, and they're not precise enough. Graphics card that is only for gaming is designed to have single precision. It doesn't have double precision. And that's not good enough for a FEM model. You need to have double precision. If you're going to do it, you have to use something like a Tesla card. And a lot of these papers that are written are not using double precision. So for it to work, we need realistic modeling. Another thing that we don't see is between the two communities of the optimizers and the actual 3D printing community is they're not validating their models. You have to validate. If you print it, if you design it in the computer, you have to print it, descriptively test it, and verify that the two are matching up. Finally, multiple load conditions. This is another one. A lot of the papers we see, a lot of the work we see is for a single load condition. If you optimize a design for one load, then it will only react to that one load and nothing else. It will not optimize. So if there's any sort of torsional forces or anything like that, it isn't evolved for that, it isn't optimized for that, and it will break. So you have to work out all the loading conditions that you need to design to react to so you can optimize it. We're working on approaches of Pareto optimization to see if we can generate better, more robust models. And finally, we have 3D printing constraints. These are other factors that can be optimized. So wall thickness, there's limitations in each 3D printing technique for how thick the walls can be and how strong they are depending on the thickness. Cooling and heat dissipation, if it prints too much in one go, it will cause contractions, and there's actually factors in the 3D printing process that can be optimized and have to be accounted for as well. And finally, support removal and cleaning. So when you print a very complex design, sometimes it's impossible to get all the support material off it. So these are things that can be factored into the model. So that's about it. So the main challenges are trying to get accurate modeling in the software, multiple load conditions, and including 3D printing constraints. So that's it. Thank you very much.